You know what that is? That's potential energy.
Well, aloha, everyone. Today we want to talk about the idea of electrostatic potential energy.
Now, you might remember from Physics 1 that in order for an object to have gravitational potential energy, first, it has to be in a gravitational field. Second, it has to have mass. And finally, it has to be held at a height that is non-zero in that gravitational field. If you let it go, that energy turns into kinetic energy.
So the same thing is true for an electrostatic field. If we have two charged particles, maybe one's here and one's here, and maybe they're both positive. If we hold those two particles in place and don't let them move, these two particles are going to exert a force on each other. That one's going to get pushed this way, this one is going to get pushed that way. So because of that, these two particles that are exerting a force on each other, when we release them, they're going to start to move. That means when we're holding them here, when we're keeping them from going apart, those two particles must have potential energy. They must have electrostatic potential energy in this arrangement. Why? Because when we release them, they will begin to move. So this has electrostatic potential energy. Likewise, if we have a positive and a negative charge, if we hold those two things in place, they're going to feel a force that is attractive. They're going to want to go together. So because of that, these also have electrostatic potential energy. Because when we release them, they will begin to move just as well. So the question is, how much electrostatic potential energy do each of these objects have, or each of these arrangements have? How do we calculate how much electrostatic potential energy we have? Well, it turns out it's based on how much force they exert on each other, and how far apart they are. So where would these things exert zero force on each other? Well, in order for the force for them to be zero, so F is equal to, we already know Coulomb's law, K Q1 Q2 over R squared. In order for this to be zero, there's a few possibilities. If Q1 is zero, the force will be zero. If Q2 is zero, the force will be zero. But if both of those charges are not zero, then the only thing we can manipulate to make the force go to zero is R, the distance between the two forces. Well, it turns out, what do you get to make this whole thing zero? You can't really think about that. But what we can say is that if we let R get really, really, really big, then the force is going to die off. Eventually, when you are an infinite distance apart, the force is going to be zero. So since the force is zero when these two charges are infinitely far apart, we're also going to define that as the place where they don't move when you release them. What that means is if you take these two charges and you pull them really, really, really far apart, ridiculously far apart, they won't affect each other. How far apart? Larger than the universe. Infinitely far apart. And when you do this, they won't affect each other, they won't put a force on each other, which means in that arrangement, they will not have electrostatic potential energy. So, the first thing to know is that electrostatic potential energy is zero at an infinite distance. The formula for electrostatic potential energy is going to be very closely related to the formula for force. In fact, they're going to look almost identical. There's only one small change. Electrostatic potential energy, we're going to use a capital U for potential energy, and we're going to use a lowercase e to represent electrostatic, is going to be given by K, Q1, Q2 over R. The difference between the two formulas? R is not squared in the formula for electrostatic potential energy. So, here is our basic formula for electrostatic potential energy. And you can see that when R gets really, really, really big, so if R gets bigger, the electrostatic potential energy will drop. Eventually, when R goes to infinity, electrostatic potential energy goes to 0. So let's imagine that we have the following situation. Let's say that there's a positively charged particle here, a negatively charged particle here. Maybe this charged particle has a charge Q1 is going to be equal to, let me rewrite that nicer, Q1 is going to be equal to, let's make it 3 microcoulombs. And let's make this one, Q2, is equal to -2 microcoulombs. And let's make the distance between them, I don't know, how about 50 centimeters? Okay, so here is our basic problem, and we are asked to find what is the electrostatic potential energy. How much electrostatic potential energy do these things have in this configuration? Well, it's a pretty simple process. We're going to use U sub E is equal to K Q1 Q2 over R. So this is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared times Q1 is going to be 3 micro means times 10 to the -6 coulombs times Q2 is going to be -2 micro means times 10 to the -6 again coulombs, all divided by the distance between them. 50 centimeters is 0.5 meters. And when I do this, I get an answer of negative 0.108. But what are my units here? Well, let's really quickly go through units. We have a coulomb squared here, and a coulomb there. We have a meter on the bottom, which will get rid of one of these on the top, and we have a Newton times a meter. Well, a Newton times a meter is just a joule. And we know that was expected, because what are we finding here? Potential energy. Potential energy is measured in joules. But Mr. Williamson, you might ask, why is this answer negative? How can we have a negative amount of potential energy? Well, remember, it depends on where you take 0 as. With gravitation being an analogy, we sort of imagine this. If we say ground level is 0 potential energy. If we have a person here, and they hold up an object, this object we would say has positive potential energy. Now, if you had this another person, if they dig a hole down into the ground here, and if you have a person here, and they have an object, very terrible drawing, but they have an object down there, at that distance, we would say down here, this object would have negative gravitational potential energy. And all this means is if you have positive potential energy, if you let it go, it will return to zero. If you have negative potential energy, it won't return to zero on its own. Instead, you have to do work to get it back up to the zero potential energy level. You're going to have to lift this box back up, climb with it, carry it up to the zero level in order for it to have zero potential energy again. Well, the same thing is true with electrostatics. Remember, we said they have zero potential energy when they are infinitely far apart. So in this example, these two charges, if I let them go, they will not naturally go back to zero. In fact, they'll be attracted to each other. So to get them back to the zero level, to get them back to an infinite distance from each other, I'm going to have to put energy into them. And in fact, if I put 1.08 or 0.108 joules of energy into these objects, turn that into kinetic energy, that will be enough that they won't ever come back together. That will be enough to keep them moving opposite each other forever. So what would happen if you're told that two objects are a certain distance apart from each other and they're putting a force on each other? So maybe we'll make them 1 meter apart, and they're putting a force on each other of, I don't know, how about 7 newtons? And we want to know how much potential energy is stored in this configuration. Well, in order to solve this problem, we think about the two formulas. Fe is equal to K Q1 Q2 over R squared. We also know UE, electrostatic potential energy, is equal to K Q1 Q2 over R. So the only difference here is an R in the denominator. So I can manipulate this equation on the left to look like this. Fe times R, so I'll move one of them over here, is equal to K Q1 Q2 over R. Oh, and this is equal to UE. So it turns out electrostatic potential energy can be determined from the force and the distance. Fe times R, assuming, of course, that the force is not changing over the distance. It gets really complex and calculus-based if you want to go a little bit more complex than that. Okay, so the electrostatic potential energy in this situation is equal to the force times R. So if I go back up here, I have the force, I have R, so how much energy is there? Well, U sub E is equal to 7 newtons times 1 meter. That's equal to 7 joules. Now things can get a little bit more complex with electrostatic potential energy. If you move things enough that they start to change the forces on each other, now you have to take that into account. And instead of simple multiplication, now you have integrals and calculus-based physics. But that's beyond the scope of this lecture. So for now, you can think of it as force times R is equal to the potential energy. So that's about it for electrostatic potential energy. I hope you learned a lot. Mahalo for watching, and see you next time.